start recording. All right, recording is active. We can go to this website here. .51.191.188. We were just getting to the good part, too. Okay. All right, sweet. Let me make sure that my right screen's being shared on OBS as well. Window capture. No, I don't want that. Okay, sweet. Okay, so this is something useful to know for Linux. If you type, any software that you would be able to access from the command line, any packages, anything like that, and you add -- version at the end, that'll tell you if the thing exists or not. Because if I didn't have GCC on my Linux machine, then it would say like, oh, I have no idea what GCC is. Actually, I'll just show you. Like if I ask it what GC is, yeah, it'll just tell you like this, and then it'll suggest you download something called GC, but I'm not going to do that. So when you downloaded GCC, you should have also gotten something called GDB, which is what you're going to be using for the next 2 labs. GDB stands for GNU Debugger. GNU is GNU. Yeah, so there you go. Pretty much GNU is just like some open source software organization in the 80s that wrote a lot of the kernel code, or not the kernel code, but like a lot of the code associated with Linux. And then Linus Torvalds, who made Linux, just like took a lot of the stuff from the GNU project and then added it to Linux. I think the debugger was made by, this is their debugger, and it's used for C, the C programming language. So if I press GDB, enter there. Okay, now we're inside the debugger. And I think if we do run, and what was the name of my program again? I literally forgot. Yeah, my file. I think if I do run my_file, starting no executable file specified, use file. Okay. So, no, did that not take? Get out, get me out of here. Okay. Let me look back at the guide real quick. GDB run and then program. Okay, so you're actually gonna run, okay. So we do GDB, we do run /my_file. That's the name of our executable. So now if we do something called layout ASM, this will give us, this will show us what our program looks like. I think if we do run, what is this? Starting program my_file, no executable file specified, use the file or exec command file, what? Is it not able to load the file? Okay. Run program. Okay, maybe you have to add it with GDB. Yeah, okay, I think you do. Yeah, I have to use the run command, I think. Or specify the binary. Okay, GDB /my_file. Okay, we're in. So pretty much what I did was I just opened the debugger and I ran it on that executable I just made, that my_file. So now if I do layout ASM, you guys know what this is? Have you guys started on this yet? This is assembly code. So pretty much, like, how I just wrote that Hello World program? This is what that Hello World program looks like in assembly. Pretty much, these are, just explaining this a little bit. This is like the actual assembly instruction, or this is like where the assembly instructions are located in memory. Because when you run a debugger, pretty much like that binary that you're running is an actual like running program on your machine, and it has its own memory, and pretty much like this is like the actual location on your machine, which is on the VM. Like in memory. I don't know if that made sense. You'll probably learn more about that in OS and like later on in this course, but for now, just talk a little about assembly. You've at the beginning of every program, you're gonna have like some push RBP instruction, I believe. That's like your int main. With that like that percent sign with the RBP in front of it. Pretty much, that's a that signifies a CPU register. So like all your machine is doing at the very end of the day, the lowest level, all your like CPU is doing is it has like a bunch of different registers in them. It has 64-bit ones, it has 32-bit ones. I think the like AX, that's like a 32-bit one. R's, or maybe R is 64, I can't remember. But pretty much your machine has like all these different registers, and it's like taking data from your CPU cache or from like your RAM and memory. It's pulling the data out, and then it's performing like some instructions here. So pretty much your computer's just doing math, and this is the way it does math at like the lowest level. Like this is the closest you can get to being like human readable without being zeros and ones. And a lot of these instructions are kind of similar to the homework and lab you just did that was working with bitwise operators, because that's how the machine operates. It does right shift, it does left shift on bits. That's like what all of these instructions ultimately are. It move, that's like, it's literally saying, hey, move. If it has a dollar in front of it, that's like an actual value. So like this is actually 0 in hex. And it's saying, hey, move 0 into my EAX register. I think Gio will probably talk a little bit more about this, but I just want to like put this on your guys' radar. So now that we have that, if I do R, why did I do it twice? Okay. So if I do R and I'm in the GDB debugger and I run it, that runs my program. It printed hello world without the H, I guess. And yeah, so then it says that it exited normally. That's always good. So now let's quit out of the debugger and let's edit our program a little to make things more fun. Oh my gosh, my terminal is bugging out today. Oh yeah, Q for there's actually this is going to be really helpful because that's literally what I was looking at. GDB quick tutorial.pdf. See, when I took this class, I was in the first group of people that took this class. Oh wait, I'm not streaming it. Pretty much, if you go on Canvas, I'm not going to change that because it's probably going to break again. If you go on Canvas under modules, there should be something called GDB-quick-tutorial.pdf. That's going to be very helpful for you guys because that has all the instructions you need to run GDB, and that's actually what I have open on the side, and then I'm cross-referencing while I do this. Like I understand how it works conceptually, but like remembering all the different instructions that are available and like all the different things I have to type in the terminal, I don't remember all those off the top of my head. So what was I going to say? Yeah, that'll be really helpful. That has quit on there. It shows you how to run it, all of that. All right, now let's go edit our file. What do we want to do to make this more difficult? Let's add a function. What? Okay, let's add foo. What do you want foo to do? You know, let's make an int. Let's just have it add 2 numbers. Whoop. Oh my gosh. I swear I'm not typing that like that. Okay. Int A, we have an int B. Okay. Wow, this is going really slow. It's probably because I'm running OBS in the background and I'm streaming all of it. That would do it. It's still trying to like select things. I literally I'm not even touching it. Okay. Okay. So let's just make some int A. Int A equal to, I don't know, 7. And then we'll have int B. I know that's not int spelled correctly. I'll fix that in a second. Equal to, I don't know, 9. Okay. So now we're going to call on foo. We'll pass in A and B. And then we're just going to have foo return adding both of these. Okay. You guys able to see this? All right, let's save that. And then, yeah, we'll close it. If we cat it, should be consistent. Okay, it looks like we want it to. Sweet. Oh, if you guys don't know about cat pretty much just it'll take a text file and it'll just print it to your terminal. It's pretty useful. Especially once you learn about pipes, but you'll probably learn that in OS or something. Or actually, no, I think you learn it in this course. A pipe is just the vertical bar. If you type the vertical bar in like this, if I type the vertical bar in Linux, I can use that to take the output from one program and send it to another. It's pretty useful, but I'll show you that some other time. Okay, let's recompile. Where was it? Okay. All right, I just recompiled. So now if I do gdb.backslash my_file. Okay, we're inside of my file now. I think I also want to show you there's a layout source, src, which I guess isn't showing it right now. And I think it's kind of a pain in the ass to set up, but if you do layout source, I think you can get side by side. You can while you're running your code, you can also see what it looks like in C. But I think it can be a little buggy. So and plus for this, you're gonna want to use layout ASM anyways because that's the level that we're working on. Okay, sweet. So now what we can do is, you see this right here? You know what's happening here? Does anyone want to say what's happening here? Yep. We're calling our function foo. So it's doing math here. It's interesting it's not doing add. Let me see if I can recompile it with, I can actually make it so it's a little bit closer to -02. Yeah, I might be able to compile it so it's a little more debug friendly, because when you pretty much, the job of the compiler, it's not to make your code look pretty and debuggable in assembly. The job of the compiler is to take your code and turn it into whatever assembly will run the fastest on your machine architecture. So there's a flag that you can pass in when you're compiling your code that'll tell it like, hey, can you make this like if I tell you to add, can you make it so you actually add it instead of doing like all these crazy like push and pop and other instructions, and it'll actually get closer to the way your actual code looks. So like I think if I pass in OG and then // my underscore file. Okay, that wasn't right. I need to remember how to set the GCC dash, where was the compile instruction I just ran? Okay. Does that work? Okay, I think that makes it a little better. No, there's still that subtract instruction in there though. Uppercase O. Maybe uppercase O? Let me double check how to run the instruction like optimized. Okay, -OG -01. Okay, so I had it right. Okay, here, let's try this. Okay. I'll need 2. Let me verify which one that got. I think that's the way you're supposed to pass it in though. Here, give me a second to like double check how you can run the optimized. Assembly optimized. Okay. I want to give you guys the right instructions. That's the thing, though. Like, I don't want to use ones that like aren't working correctly. Could look back at my notes for this class. That actually might have exactly what I need. Yeah, when I look back at my notes for this class. Nope, not that. Okay. Okay, that's it, I think. Okay. GCC -O2-S. I think this is going to save the assembled code though. And then what I call it, my underscore file.c. So it saved the .s file. Yeah, that has the actual assembly instructions though. That's another thing. You can actually prompt it to like actually give you the assembled code for whatever executable you have. So that's what I did. I just compiled it and I turned it into assembled code. I gave it this -O2 flag. Pretty much it's this -S flag on the GCC compiler. When I add that, it's going to give me this .s file, which is effectively just like assembly instructions. Of course, it looks different than the ones you are used to, but it also has some optimization flag there. Okay. Would that only generate a... I have to link all these? Okay, I think that's the right thing. Okay, I think this should be the right thing that we have to put in the terminal. See, as you can see, there's a reason I didn't remember this because it's a lot. Let's see. What did this do? Okay, there's our binary. Let's get rid of that assembled file. I don't really want that anymore. So now if we run my underscore file, we do layout ASM. Okay, I think this is, yeah, this is a little closer to the instructions we want. Doing here, oh, it's bit masking. Something I did want to show you guys is you can add breakpoints. What happened to my function? Start. Yeah, so you can add breakpoints to the program. So like, let's say I want to add a breakpoint at like here. And then I can just be like, oh, hey, add a breakpoint, right? Not defined, no. You know, it might be better if I use the old one, honestly. That sounds kind of bad, but GCC. Okay. So if I do this, and then I do gdb.\my_file, I do layout ASM, I should have. Is it not calling on that function anymore? What is my hold on. What does my code look like right now? Yeah, it still has int foo. Okay. Oh, uppercase O, that's why. Okay. gdb.\my_file, layout ASM. Okay, we're back. So we're calling this function foo here. So like, let's say I want to add a breakpoint. I do B for breakpoint, or you can just type breakpoint. And then you say, hey, I have a function called foo. Let me add a breakpoint there. There you go. Okay, you just added a breakpoint. So what is a breakpoint? You guys just got a lab, right? And for that lab, it's, I don't know, what does Giovanni call the lab? Because he says he doesn't call it this anymore, but we called it the bomb lab when we got it. And pretty much the reason it's called the bomb lab is because, like, let's say I want to run the program, right? And if I just do R and I do run, then I should go all the way through the program and it'll say, oh, I exited normally. But with the bomb lab, you won't exit normally. You'll get -2 points on the leaderboard and everybody will see it. So what you do to not get -2 points on the leaderboard, which will affect your grade, because the grade that's on the leaderboard, like the grade that you see that's on your leaderboard, or sorry, the grade that you see that's on the leaderboard is going to be yours when you turn the assignment in. So the way you don't lose points is by adding breakpoints in the code. That way you hit the breakpoint instead of the end of the program. But with the bomb lab, you won't hit the end of the program. You'll hit some bug that's going to like obliterate your program. Yeah, it'll crash the program. That's why it's called the bomb lab. So I'm giving you guys like that advice now. There's going to be points in the code where you're going to want to add breakpoints. That way you can not hit them, not hit the bad parts. So if I run the program right now, it should run it, and then it says, oh, I hit breakpoint 1. So instead of hitting the end of the program, now I just hit foo, right? So what do I do once I'm inside? Now I'm actually inside of foo. So like if you look at the instructions here, I'm actually inside of the function foo as I'm debugging it. And like what's going on here is I'm actually like, I'm running that executable, that binary file that's all like zeros and ones. And this is what the assembly looks like in real time while I'm doing it. And I can just choose how fast I want to step through all the instructions of that binary. So like there's actually a process running on my machine is essentially that my_file. And this is how I go through it line by line. So you have SI and NI. Let me explain those. And I'm actually going to open the GDB tutorial to give you exactly what it says, and then I'll explain it a little bit more from there. So you have NI, which stands for, you could also type, it's a next I, which is this instruction. And what that does is it will runs the next line of assembly code and does not step into functions. So what that means is NI is what you do when you just want to get around really fast in the program. So like when you're doing the bomb lab, you're probably going to you're going to mess up a few times. Trust me, the lab took me 19 hours when I did it. You're going to mess up a few times. So when you want to get back to where you were before, you're going to probably be going really fast because you're going to be like, okay, I've been here before. Don't care. You're just going to be spamming it because you want to get to where you were before. You're probably going to use NI then because that just skips over functions. So like if you don't want to step into every single function call that's being made, like if you do, so that brings me to the other one. There's step I. Maybe I should start with this. There's step I here, and pretty much what this will do is is, and let me read the instructions. It steps through to the next line of assembly code, and this will step into functions. Or you can just do S for step. So, like, if I did step I, if I was at the instruction right before foo and I did step I would actually go inside foo. So this can be kind of a blessing and a curse because maybe you wanted to go in foo, so now it's good that you're inside. And there will actually be points in the bomb lab where it's useful to step into other functions because, like what's inside of that function is what you need to get to the next phase of the bomb lab. There's 6 phases to the bomb lab. And like you might like pass over a function and you'll be like, oh, maybe I should go inside of that and see what's in there. And then like when you're in there, you get like some clue as to what you need to pass that phase. But sometimes it's just unnecessary. Like you don't want to step into a printf statement because nothing exciting is going on there. That's like a system level call. So I think you can step out. Like there's ways that like if you get into a function like a printf that's like you know what it does and it's useless being in there, then you can actually step out of it, which I think is what next does. If you run next, I think you should be able to step outside of the function. So like if I run si for step into, I go to the next line in foo, right? Say I want to go in. Okay, more instructions, we don't care. So then if I run ni, okay, so ni is still going to take me through, but I think there's a way you can step out. Is there a way you can step out? Next just runs the next line. What if I just run next? Okay, yeah, so if you just run next, that'll just step you out of that function. So you see how like right now I'm at literally the instruction right after foo here. Like foo was the previous instruction I was at, and now as where it's highlighted, I'm at the one after. If you just run next, that'll just step you out of the function you're currently in. But because you're running an actual binary, you can't go back. Like you're running this code actively, so like when you run that, you can't really go back. I mean, I think with like other more modern debuggers you can, but not this time. If we do step, si, we're in int main. Also if you just hit enter, I think it runs the previous instruction. Does it? Oh shit! Whoops. If I run si, yeah. So I can just keep running si, keep going. Eventually, it'll probably just hit the end of the program. Right now, this is like not even in, I mean, this is like our code, but this is like other stuff. This is like operating system level stuff at exit.c. Yeah, like this is like operating system level stuff. So if you start getting to like a point where you're like, where the hell am I? You're probably like in system, you're probably in like system level calls being made. And at that point, for the scope of the assignment, like if you're doing the bomb lab and you start seeing like anything like double underscore, if you start seeing double underscores, you should probably be scared and like get out of where you are. Not scared, but it just means you're not in the right place. Like anything double underscore in Linux and in C means like internal. It means like you're running like at the operating system level. And you'll learn about that stuff in operating systems, but for the purpose of this class, it doesn't really matter. Oh yeah, sometimes, okay, it's good I did that. Sometimes your screen will completely bug out. Like, you see how that's like clipped right there? Like that, that's not supposed to happen. That's just because I kept pushing it. Sometimes like where I was inside of that run underscore exit underscore handlers system call. And eventually I got to a point where I was no longer in there. And now I'm in this underscore DL underscore finish, whatever, I don't know. I'm in some other function. And once I got to that other function, it kind of like, it like broke the debugger. It's not really broken. It's still running fine. It just broke the layout. You can type ref for refresh, and it fixes it. And you're still in the same place, too. So that's pretty useful to know, ref. Don't run R. R is run. if you hit R, that's like, that might run you, if you're doing the bomb lab, that'll run you like too far into the program and it'll crash it. So REF is different. That just refreshes your screen if it bugs out, which it probably will a few times, because anytime you jump around functions, that's gonna happen. And there's a few different functions you're gonna be in the bomb lab. Let's do SI, we can just keep doing it. Yeah, see, we jumped again, now we're here. It's interesting, now that I'm doing the bomb lab now, I kind of understand some of these functions because I've already taken operating systems. Yeah, there's also continue, which will continue the program until you hit the next breakpoint. So like, if I do that, that'll run to the end of the program. But let's say I wanted to go and edit my file. Let's add another function just for fun. I'm gonna call it bar. I don't know. Let's have this like multiply two numbers. Yeah, okay, let's call bar. So now if we compile it again, A dot out, if I run that, that does compile it the right way, right? Okay. Well, so I'm not like just spamming through like the terminal and you guys have like no idea what I'm doing, right? Has there been anything up to this point that's just like been like a brain breaker? Yeah, what's up? What, sorry? What is it? No code available? You're following through.
Yeah, I mean, I lost you.
So like, here, just hit Q, yeah. Does it say that you're inside of the, okay, so you're not like actually running it though. Here, type ls. Oh my gosh, you have a lot of, myfile.c is there. You have the myfile executable? Because I don't think I see it there. No, okay, so you need to compile that with GCC.
That I did.
Yeah, but that when you no, that's not right. That's you need to run GCC. Here, I'll go back and you can copy it.
If I do the one you did, it just says wrong.
You want to run this. Okay. So there's a difference. GCC is the compiler. The compiler's job is pretty much to take all your C code is. There's nothing special about your C code. It's literally just a text file that has .c appended to the end of it. Like it's just text, okay? That's all code is. It's just text. The compiler is what makes it more than text. It's what's able to take it. It has some set of rules, and it uses those rules to take that text and turn it into an executable file. And pretty much when you're coding, you're just following some set of rules that the compiler is like, like if you're missing like a semicolon or you're missing like a curly brace or something like that, the compiler is going to complain about it and tell you can't do that. If it's a good compiler, it'll tell you which line you messed up on. It'll tell you why you messed up. C, the code that we're writing, can be a little less forgiving. You'll get seg faults and memory dumps and stuff like that. Like you're actually dealing with actual memory management. With like Java or Python, you're not going to get that as much because it's kind of like a layer removed. But at the end of the day, Java and Python code just ends up becoming C code anyways. So you're kind of learning like how it actually works under the hood by doing this. Or did you get that instruction? Did you run the GCC command?
Yeah, I did, but
It didn't work? What did it say?
it says no source error button.
No, wait, what happens when you run that GCC command that I highlighted though? So if you type that is, okay, so then you do ls, so that binary should be there now, right? You should have an executable called my_file. Okay, yeah, that just got you, when you ran it, it created that. So now you want to run that.
Yeah.
Yeah, but you're inside of it now. Oh, you're doing layout source. You got to do layout ASM.
Layout?
Layout ASM for, like, if you want assembly. You want the assembly layout. Layout source will give you, like, the layout just means it'll give you, like, a side-by-side, like, while you're running the code of, like, what's happening. Source will give you the C code, but you don't want to use that for this course. I just did that because I could. Layout ASM is the one you want to use because that gives you a layout of the assembly instructions. Anytime you see ASM, it means assembly. So, you gotta go. All right, see you. Good luck. Sweet. All right, does anybody else have any other questions, like up to this point? Have I just been have I just been like typing into the terminal? Is it like some magic black box, or like is anything I said like up to this point like made sense? Yeah, what's up?
Should I be getting main inside the binary, or should I be getting something else? Because I'm getting
Should you be getting what?
but here I'm getting not main. I don't know, and it says something else. Is this right? Because my code.
Oh, you stepped in. Oh yeah, you stepped into it though. Here, go back. Hit Q. Okay, and then run. Okay, here we go. Yeah, like you were. What? What was the difference? That was old. Like I think you stepped into it a little too far. And you were in like OS. You were in like OS system calls land. Like I think you went too far into it, and it just like you must have run it, and it went to somewhere else.
Okay.
Yeah, it's pretty easy to get lost out here. Like you want to be where things are familiar. Like you see function names and they're actually like human readable, like foo, bar, function one, fun one. Like that means that you're like in the right place. Once you start seeing once you start seeing double underscores, that's probably when you're like, okay, I went a little too far. So that's when you run n. That's when you get out. Any of that. I mean, you might see them like here and there, like in regular code, but I'm just saying that probably means you're at like system level things happening. Like you went inside of a printf. And like, hey, what's up? GCC, my file .c-o minus. You have the. Oh, you just have the binary. What happened to the .c file though? Oh, that is the C file. You're just .c. It recognizes it's a C file. Yeah. So the thing with Linux is anything goes. Okay. So like if I want to say that my C file is like, whoops. You gotta go. Okay. So like if I want to say that my like .c file is a .cpp file, which is C++, then I can do that. If I want to say it's ABCDEFG, so on and so forth, I can do that in Linux. Like in Linux, file extensions don't really mean anything, but to the compiler they do. Like to the GCC compiler, which is the compiler for the C programming language in Linux, the most common one. It needs to have that .c ending at the end of the file. That way it knows that it's like, that way it can say, this is text, but this is special text, this is C code. And then it turns it into an executable. All right. Any other questions? Okay. So you can add breakpoints at specific lines in assembly code. Let me check how to do that real quick. List, no, where is it? Breakpoint. Okay, yeah, I think you had the pound, you had that in front of it. Okay, yeah, that's easy. GDB /my_file. Layout ASM. Okay, here, let's just add a few breakpoints in here just for fun. Then I'll also add one in there. That's, I'll also add one in here that's going to be at like just some random point. Here, let's add one like right here. Okay, so we added a breakpoint at foo, we added a breakpoint at bar. Let's add a breakpoint right here. Sweet, that's how you do it. You just put the little asterisk in front of it. And then I just added a breakpoint right here. It also has a +b. So this assembly instruction right here, 0x181, I just copied it, and then I said breakpoint, star, or asterisk, and then just that actual location. And again, I just looked at the GDB tutorial, and I was able to kind of like figure out like, oh, I can add breakpoints at like this specific memory address, and it lets me do it. So now if I type R, this will give me a chance to show you what C does, like that C for continue command. So if I type R, what do you guys think it's going to do? What? Yeah. And by the way, breakpoint 1 doesn't mean it's the first. In this case it is, but it just means it's the first one you added. If I do B space I, which is breakpoint info, never mind if I don't do that. Yeah. Is it no, I think it's I space B. Yeah, so this will just list all the breakpoints I've active. This is useful. You're probably going to have like 3 or 4 breakpoints active at any given time for the bomb lab. You're going to have to remove them. So like the way the bomb lab works is you're going to have 6 phases. And obviously you're going to have a breakpoint at like phase 1, right? Like there's probably going to be like a function called like phase 1. There's going to be a function called like bomb or something. So you do B space bomb or whatever it's called. So now you have a breakpoint bomb and you have a breakpoint at the end of phase 1. And eventually you're going to get through phase 1. You're probably going to add your solution to phase 1 to this text file. And then after that, when you get to phase 2, if you still have that breakpoint on phase 1, every single time you run it, you're going to keep hitting that breakpoint on phase 1 again, like over and over. So it might be useful to remove that old breakpoint, which I'll show you how to do in a second here. But like just I space B, which is the same as like info, I think breakpoint singular. Yeah, info breakpoint. That I space B is just this. Like I've been using all these like little shortcut like names like SI, NI, NS, all those. You can type out the full thing if you want, and it'll still show you the same results. Like you can type info breakpoints of I space B. It's just faster to type I space B. Yeah, so this will show you what all of them, like it's going to show you the memory address, it'll show you the breakpoints enabled, it'll show you like where the breakpoint is, and that's actually cool. So like it'll tell you, oh, this is int main plus 41, and that's actually inside of int main. It has that plus B next to it in the assembly view. Something else I could show you. Disabling breakpoints. Is it just D for disable? Okay, yeah, so if I type R, I'm gonna hit breakpoint 1. Where am I? Where did I go? Oh God, where did I end up? Warning, cannot insert breakpoint 3 memory. Uh-oh. Or wait, where are we? Cannot find bounds of current function. Okay. I don't actually know what just happened, so we're just gonna bail out of that one. That happens in assembly. I wouldn't be scared. If things start not working out as expected, you can always just quit the program. There's no consequences there. Something to note, when you add the breakpoints, you're adding those on that actual running binary. So now that I did quit, I'm no longer running that binary. So in effect, those breakpoints don't exist anymore. If I run the program again, I'd have to re-add those breakpoints. That's also useful to note for the bomb lab, because if you had breakpoints to like right before you set off the bomb, and you like need to restart for whatever reason, then like you'd have to add all your breakpoints again, which isn't as much trouble as as it sounds like. You just do like B space, whatever 2 places. What's up?
So all the locations would stay the same. So if we're to like
Yeah, they wouldn't change. Yeah, actually, the binary is still the same. Like if I run GDB space / my underscore file again, it should. Did I crash? That would be really unfortunate if I crashed. Yeah, so if I ran that again, I think I crashed.
So in the lab files, there's a C file and there's a binary.
Is there a C file?
Yes.
Okay.
Like it contains just functions, and like, if you like clear the functions, it prints out the message that you have cleared them or something.
I think the C file is just there for hints. The binary is like the main assignment.
Do we have to make changes to the binary?
No, you cannot make changes to the binary. You might be able to, but I don't know how to do it.
What exactly are you supposed to do with the binary?
You're supposed to run it, and you're running it in the debugger, so you're adding breakpoints to it. The binary is not changing. The binary is just some C file somewhere that's been compiled, and like pretty much that binary is not changing at all. You're just when you're running through with the debugger, you're not changing it. You're just you're like inspecting it. When you add a breakpoint, you're not changing it. You're just kind of like it's just a way to inspect it. And actually, debugging, it's really useful when you're actually like in industry and you're on your co-ops. It's used a lot in software engineering because it's how you figure out issues. I mean, it's not going to be at this low of a level where you're doing it in assembly, but this is actually like at a very low level what's happening when you're debugging. You're just going through assembly instructions. I mean, debuggers are written by like insanely smart people like Microsoft and stuff like that. And at the GNU Open Source Software Foundation, where there are people who are able to somehow like match that, oh yeah, all these zeros and ones of that binary that you're running actually match over to this assembly instruction that's being run on your CPU. And I think that's like pretty impressive engineering feat within itself, that someone was able to like actually match those assembly instructions that are happening over to like the binary that's running on your machine, because your machine understands the zeros and ones, but you understand the assembly. Well, I mean, you should by the end of the course, supposedly. But I'm gonna have to restart this though. Power off my machine. So I'm probably gonna lose sight of that real quick. Any other questions like up to this point though? I'm starting my machine up here.
So like in addition to like adding breakpoints, what do we have to do with that? Like what exactly do we have to we do like run the like binary using the GDB.
Yeah, you're running the GDB debugger on the binary. It's like attached to it. And then, yeah, you're running the GDB debugger on the binary, and then you're just setting breakpoints on it, and then you're just stepping through different, like, various assembly instructions and trying to find out, like, what's actually happening under the hood.
And then what gives us points?
Like, getting through, like, each phase will get you more points. What'll lose you points is if you step into the bomb. So once you, like, you hit that breakpoint that says, oh, hey, like, you're in the bomb now, or like you start seeing you're in the bomb, then it's time to bail. Let's just quit the program, run it again, or rerun the program.
And the instructions to clear each phase would be like you would get them after like running the binary.
What, sorry?
Like what do you have to do to clear each phase? Like,
So there's gonna be like a text file, and pretty much for each phase, you're gonna get like some kind of passphrase. Like it might be like some numbers, it might be like a phrase or something, or like a sentence or something like that. Pretty much, it'll like print out to your terminal, and you'll see it. It'll be like something completely odd, like 717, or this is like something you haven't seen before. So at that point, yeah, what's up?
So, are there any commands in Linux that we're not allowed to use?
No, I don't think so.
If we step into the bomb, and I found a command line to go back a step, do we already lose the points? Or is it once we step out of the bomb?
It's like when you hit the bomb, it's gonna crash the program. So it's anything before that doesn't really, I think it doesn't matter. Yeah, I mean, I don't think there's anything you could do that.
You see in the program, you have to step through all the bombs.
Well, you're stepping through all the phases, and then the bomb is the thing you're trying to avoid.
So we're not actually modifying code, we're just stepping over things.
Yeah, pretty much.
Like setup.
Yeah, this is actually kind of a useful exercise because it's teaching you how to like inspect things. It's like you're investigating things. But yeah, you're not actually writing code. You're learning how to debug, which is probably the most useful thing you'll get out of this class. That and like knowing how Linux works. And on that note, let me like get Linux back up. Okay, what's our code? 2664. Owen, sweet. Share screen. Where is it? I have like a million things open, which is probably why it crashed. Running, okay, allow. Sweet. Get out of here. It's a pop-up. No, I want to go into downloads. Oh, that's another thing. If your terminal gets too large or there's too much stuff in the way, you can just type clear and it clears all the stuff above it. I think that's helpful for me to get like peace of mind, especially if I see like a million errors above and I just want to feel like I didn't just fail a million times, and I'll just run that. Well, if you keep pressing up, you guys know about like pressing up and pressing down in Linux. It just shows you like all the previous things you ran. Pretty useful. Also, if you start typing like. If I start typing something, like whatever, and I hit tab, it'll like auto-complete it for you. That's also really useful. So if I type GCC space and then I hit tab, it'll like be like, oh, you want to do this. And it kind of is able to like guess that. So that's pretty useful. gdb.backslash my_file. No debug symbols. Yeah, I mean, I'd expect that. There's nothing there yet. Let's add a breakpoint at foo. Let's add a breakpoint at bar. Let's run the program. And okay, we hit a breakpoint at foo right here. NBR64. This is end breakpoint. So that's another thing. That's like the way that it knows. Again, you're not really modifying the binary, but that it does add that just so like it knows that's like the end breakpoints. It's whatever. What's something else I could show you? Oh yeah. So if I type the C command, if I type argan, that would just rerun the program. I'll show you actually. The program is being debugged and has already been started. You like to start from the beginning? That's what happens when I type R and I type run. So if you type R, it'll always try and rerun the program. I don't want to do that. because I want to keep going. R is just to start the program. If you're at a breakpoint and you want to go to the next breakpoint, you don't do R, you do C for continue. Or I'll just type continue, because that'd probably make more sense. So if I do this, I should go into breakpoint 2, which is in bar. And then if I did C again, I have no third breakpoint. I hit the end of the program, exited normally, which won't happen to you in the bomb lab unless you complete all 6 phases. And yeah. I'm starting to lose my voice, so I'm gonna have a yogurt real quick while I answer any questions you guys have. I think there might be some other stuff I could go over. I got a banana too. Do you guys have any other questions? Nobody? Let me see if there's any other instructions I can run here. Breakpoints. Oh, there's watch points, print to screen. That's another thing we can do. Here, let's do that real quick. Let's rerun the program. Okay. Well, if I type R, it'll keep all the breakpoints. That's another thing. If you do R, then you'll still maintain all the breakpoints that you had before. You don't have to like exit out. And also, like if I type IB, it should say, okay, all my breakpoints are still here. It's also useful. Breakpoint, already hit breakpoint 1. If you type IB, it'll tell you which breakpoints you've already hit. If I want to remove a breakpoint, that's another thing. I would type just disable and then the breakpoint number. So I would type disable, and you're not going to type disable and then like the address, or you're not going to type disable foo. You're going to type disable 1 to disable breakpoint 1 that's located at foo. So yeah, if I do this and then I type IB, we shouldn't see breakpoint 1 anymore. What? I think it's because we already hit it. Maybe if I do, it should have disabled that, disable 1. Why didn't it disable that? Oh, delete breakpoint according to where they're located in the program. So clear and then the actual location. Maybe that didn't work. Okay, so if I do clear and then this, that should delete that breakpoint, I think. Oh, clear bar, or actually I want to delete that one. If I do clear and then foo, okay, that got rid of that. So I did clear and then I did foo, which was the name of the function that had that breakpoint. Breakpoint 1 is no more. As you can see, only if I do IB, only breakpoint 2 remains. It actually even says deleted breakpoint 1. Here's another thing you can do. There's something useful, and when you use a debugger in like Visual Studio or something, you'll probably see something called watch points. What that means is you say, and these are also really useful, and this, you're probably gonna be doing this a lot in the lab. You can track variable, like at that point in time, you can track what's happening to variables. So like I had, like let's say I have some variable int A, and then int A, I perform some operations on it. It's like initially int A is equal to 7, and then I multiply that by variable B, it's like 9, so it's like 7 times 9. And then I want to like shift it by 3 bits, and I want to do a bunch of other things. Obviously, variable A is going to change its value, so I can use P, which is short for print. And what it's going to do is, as I'm stepping through the assembly instructions, it'll actually show me what the value for that variable A is at that point in time. So when I start, it's 7. When I multiply it by 9, it's 45. 7 times 9 is 65. So like, you know, as you perform operations on that variable, you'll notice the variable will change in value. That's useful. You can also use it to inspect like the actual hexadecimal value of the variable. I think if I'm inside of here, there should be a variable called A. I think. Anyway. Here, give me A. I think if I print 2, what happens if I do it again? It's probably just going to say 3. It's just incrementing it. There's a way you can print actual variables. Let's just watch points, printing value, P, any valid expression. Do I have to print the pointer to it? And you have to format it. Okay. So for some reason it doesn't have that variable A. No symbol A in the current context. Yeah, but I think foo should still have a variable called A there, because I was performing, maybe not. You can also check what's like in the registers. So if you want to print like, oh hey, what's in the EDX register at this moment? Never mind. What's in the EDX register at this moment? It'll be like, oh, that. It's actually kind of cool. You can actually check like what's in the CPU registers at that point in time on your PC. I mean, there's only a handful of CPU registers on your physical machine, so like I think it's kind of interesting that you're seeing like what's actually happening with the math on your computer, with like what's it I think it's an arithmetic logic unit, ALU. The ALU on your computer is the thing that's like performing all the operations in your CPU. So you can actually look at what's happening there. Yeah, TAs are people too. What do you think? Here, print A. If I don't print A here. Maybe I should make a global variable and that'll let me do it. Gedit my file .c. Here, just make int c equal to, let's make it a, yeah, there we go. Now we're cooking. I think that's allowed. I might be wrong, but. So if I compile that, oh, it's going way back. Where are my GCC instructions? No, before all that. Okay, GCC my underscore file dot c dash o my underscore file, I think. Yeah. ls run the my file. Okay, we're in layout ASM. Let's just, like, I don't know. Breakpoint at foo. Or it's at a breakpoint, like, right here. That's right, you gotta add the star in front. Okay. So if we run and we go here. As it would turn out, that wasn't such a good idea. Okay, you know what? You know, I said you could add breakpoints at specific memory addresses. You can, just don't do it that way. I think you're better off if you just say, like, breakpoint at, like, main 4. No. Yeah, yeah. No, wait, you gotta format it, that's the thing. It has to be cast. Print. So print, and then char star C. What? What did it say about C? C has unknown type, cast it to its declared type. Okay, so there we go. Okay, I think you just have to cast it. That's the main thing. Look at that. We got C. And the reason I got it there was because I made a global variable. And global, I don't know if you guys know, but global variables in C, you shouldn't use them. I don't know if Giovanni explained them why yet, but he probably will. They live in like a separate space in memory than all the other variables. Same thing with static variables. I know about Java though. I probably should. You guys know about static variables? What? Okay, like a static variable, what's up?
Just, it doesn't change, right? It's like declaring a constant.
Kind of, not really. Like,
Save across classes or something.
yeah, so it has a lifetime, pretty much like a static variable has a lifetime longer than a, actually, that's actually a really good point. Now that kind of brings me to what I was going to do before. So with a normal variable, and you'll learn about this, you have what's called the stack and you have what's called the heap. Giovanni will explain both of these. You know, you guys are probably going to learn a lot if I just like explain this to you like right now. Normally, when you have a local, you have what's called a local variable. So that's just like I have int main, or I have so, let's say I'm inside of a function foo, right? Actually, why don't I just show you in code? Here, let's go here. Gedit my underscore file dot c. Okay, so like I have some int c is equal to 9 or whatever here. What happens to this int c right here inside of this function when I get to the end of the function? Well, no, like what happens to the variable? Like what happens to it when I get to the end of the function, like in memory? Yes, gone. It gets blown away. It gets deallocated. That's the word. Saying it gets blown away is more fun. So, pretty much when I'm inside of this function, when I'm inside of a function and I get to the end of the function, my variable, any local variables I had within that function, they get axed, they're gone. Those are local variables. Those are what we call variables on the stack. The stack is just like your main memory. That's like normal memory. You have like all your memory is like stored in a stack pretty much. And then you have what's called memory that's in the heap, which is a different part of memory. And it's not to be stack is not to be confused with the stack data structure. It's a common misconception. In data structures, you have stacks and queues, right? I think you guys are in data structures. You have stacks and queues. This stack, although it is a stack data structure, it's a different concept in like operating systems and computer systems. We're talking about the stack is like a physical thing in memory, or not physical. It's like a thing in memory. The stack data structure is like a separate, although they're kind of related because like again the stack in memory is a stack data structure, but stack data structure is like a concept in data structures, and stack in computer systems is a concept in memory. So when I get to the end of this function, int c gets blown away. Okay. So if I have this, what do I do? How do I do this in C? If I do int c is equal to int malloc. Malloc is, you guys ever use new in C++ or Java? So if you use the new function, yeah, or not new function, sorry. Just like the word new, the keyword new in C++. What it's doing, anytime you use new, you also have to use delete with it, right? I think it's delete. Yeah, that's why. It's because the professors here don't teach C++ the right way. Yeah, if you get to end, I'm honestly. I mean, if they're not, if they teach you new and they don't explain deallocating memory, there's no point of them even having taught it, or they don't know what they're talking about. So anytime you say new in C++ or Java, it's the same as saying malloc in C. And what you're doing is you're saying you do malloc int pointer, I think. 9, I think. I think I can give it a variable. I'm trying to remember how to do this. I think that's right, then you do like c is equal to 9 or something like that. You do something to this effect. Pretty much what malloc is doing, it's short for memory allocation. And you're saying, hey, can you give me 4 bytes of memory? Can you give me an integer? Can you give me an integer in memory of like this many bytes? In this case, like integer number of byte or pointer number of bytes. Can you give that to me from the heap? And what the heap does is when I exit this function, that int c will still exist. So anytime you type like new in C++, like you say, usually you do it for data structures. So you say like new vector or something. Like when you leave that function, you come back, that'll still be there. So, but the thing is, if you do new, then you also have to do, I think like dealloc or something. I can't remember what it's called, but you pretty much, there's a function you can call that deallocates the memory. So you're actually physically allocating like integer number of bytes from the heap, and it's yours, and you have to deallocate it manually. But it does serve a purpose because now if you leave the function, it'll still be there in the heap. Static kind of works the same way, where if you put the word static in front, it changes the lifetime of the variable. So like, let's say I have like static int, like let's say I had like you know, like static int c 9, and let's say I called like foo here, okay, and then let's say I also called like foo again here. When I return to foo again, c would still be like, I don't know, like c would still be 9, I guess is what I'm saying. Like when you enter again, like let's say that I did something. Let's say that foo had some logic in there that made it so like every single time I was in there, like things were different. Like what I'm saying is the static variable will always still. Trying to find the right way to explain this, but like its lifetime is. It would still always have the same value even after you leave the function. It'll, whatever it was when you left is what it'll be when you return. Is what I'm getting at. So like it still exists in memory. Now there's another thing I should teach you guys. This might be useful. You guys know about pass by reference and pass by pointer? And pass by value? You do? Okay. Should I go over it then? Actually, this might be something, I might do it on godbolt.com real quick. What was I... Do I have anything else I was going to cover here? Print, backtrace, I don't know you guys need that. You can add watch points to variables if you need to. I don't know. Like a watch point just lets you track a variable like as you're going through the program. All right, see. Here, let me power this off, and then I'll show you something else real quick that might be kind of interesting, and then I'll probably be done. Because I've talked, I've yapped for 2 hours now. What's the code? 2664. All right. Yeah, I know they're using my data. I don't care. Oh my gosh, have they changed this? Okay, let's close that. I don't want this. Let's go to C. This will literally, this website's pretty cool. It'll show you like what code looks like side by side assembled. No, I don't want that. I want source 2. Okay. Give me C code and give me... No. You gotta go. I got you.
Thanks for showing all that.
Yep, problem. I think I could put these side by side. Yo, this website's awesome. Okay. No, I don't want this. Here, give me... I want it to show me the compiled. Okay, so let's say I got int foo, int a, comma int b. Return a plus b, right? We've seen this. Int main, return 0. And then we got foo, Okay. So we got foo right here. This website's pretty cool. It'll actually like highlight the assembly instructions for you, like side by side. So like this right here, this line is in A being created. Pretty much, you see how it says RBP -4. It's taking that RBP CPU register. It's moving it over 4 bytes. That's because we're declaring an integer, which is 4 bytes. So literally, like that CPU register is moving over 4 bytes because it wants to make space for that integer. And it's pushing 9 into, like it's like saying, hey, RBP register, move over 4 bytes because I want you to make room for an integer that's 4 bytes, and then I want you to move the value 9 into RBP -4, right? So it's like the actual memory address. This is like what's happening in the CPU registers. D word just means like that it's an integer. It means a double word. It's just fancy language for integer, or it means like 4 bytes. I think like a single word, if I had just a word, instead of D word, if I had word, that would be like a short because it's 2 bytes. So right here, oh, does it not have the, does it not have the assembly side by side? This is GCC. Output. No, don't do that. We wouldn't want that. Intel ASM, no. Overrides, no. There's a way you can usually get it to have the I don't think I want it to do Intel though. Yeah, this is like what yours is gonna look like. The other one's Intel. There's like 2 different types of assembly. There's Intel, and then I can't remember the other one, but this is the one that you're using is the non-Intel one. Demangle identifiers. That might be useful. I don't know. Filter. I wish it would give me the assembly side by side. Actually, we could go to the GDB website, or the GDB compiler website. Okay, let's just do what we did before. Int foo, int A, int B, return A plus B. I don't know. There's a method to my madness. I know. In my mind, I know what I'm doing. Okay. So if we run this in GDB mode, debug, can I add a breakpoint here? Is it let me add breakpoints? Yeah, okay. Normally when you're in code, this is how you add breakpoints. You just go to the left. It gets a little red circle. That's your breakpoint. You're not allowed to do that because you're like in Linux and you're debugging it from the command line, but in effect, you're doing the same thing. So if we go int A equal to 9, int B is equal to 4, and I debug, I'll just add something here. Yeah, 3, that's fine. Debug. I know how to use a debugger. You gotta go? Alright. So, where am I right now? Just ran it. Run. Alright, we're at breakpoint 9. So if I do, hey, give me the, yep, you're welcome. I can tell it, hey, print me the memory address at A. Can I do that? Yo, it just bugged out hard. Cannot print the memory address at A? Why not? Okay, maybe just like step over. Because A hasn't been allocated yet, that's why. Okay, so now if I do PA, it should be like, okay, A is 9. If I do P star A, it should give me the memory address for A, right? I mean, you can't print the memory address at A. Star X 9. Should be able to. Maybe I could do, what's it? A. Okay, so this is our memory address, right? That's B38, okay, remember that. So pretty much, if I do step into, and I go step into here. Okay, now I'm inside of foo, right? Okay, I'm inside of here. So now if I do a print A for me inside of here, you're gonna see it's B0C, right? What was it here? B38, right? And now it's B0C. It's different, right? So if we do this, oh, I gotta edit the thing. Stop. If I do this, then I do debug. Oh yeah, that's right, because these are. Debug. Okay. So now if I do, here, let me continue. Run, okay, we're here, step into. So if I do print A, well, we got B30, right? So now if I go up to here, and I do print A, oh wait, is it not the same? Oh, I messed it up. They're supposed to be the same. I think I did something to mess it up. Oh, wait, no, I didn't. Print, yeah, B30. Okay. Yeah, so the memory addresses are now the same. And what that means is normally when you declare a variable and the parameter, it like creates a whole new variable even though you passed it in. What I did is I literally just used the same exact memory for it.
So normally do we pass it by comment or by reference?
Yeah, you can do pass by you can like add the ampersand in front and you're passing in the actual memory address. I'm probably going to stop showing the other classes about the comment, but I just wanted to show you that's something you could do. All right, let me stop recording.